So for the cooling of a disk, we have basically the same setup. I'm using R instead of rho because it's the cylindrical radius instead of the spherical radius. But other than that, things look pretty much the same. We're fixing the outer boundary to have temperature 0. And then the only difference is instead of it being a uniform temperature all the way through at time 0, it can be something that depends on the radius. And so the first thing to do is to use the radial Laplacian. So we can rewrite the equation as ut equal to k u sub r plus 1 over r u sub r. And it's curious to note sort of what happens here, because in the last one we were looking at, we had k u rho rho plus 2 over rho u rho. And that 2 somehow makes a huge difference, because in this one you can make the substitution v equals rho y, and everything just cancels out absolutely beautifully. But if you try and do something similar here, it turns out just not to help you at all. So things become a bit more complicated. Let's see. So doing the usual thing and applying separation of variables, so we get y of r g of t, and substituting this in, we get g prime over kg, so we're going to get a decaying exponential for that one, just like usual. And then we've got the y double prime plus 1 over, yes, sorry, that's right, plus y prime all over y equal to r minus lambda. And then that's going to give us g prime equals minus lambda kg, and y double prime plus 1 over r y prime plus lambda y equals 0. And this one is known as Bessel's equation. In fact, it's the 0th order Bessel's equation. So we can multiply it through by r, and then rewrite slightly, and you notice that this is ry prime prime plus r lambda y equals 0. So this is now a Sturm-Liouville operator with p of r equal to r. And so since this function takes value 0 at 0, it is a singular SLP. And note also that we've got a weight function of r as well. And so earlier I used r for the weight function following the book, so I can't use that right now. But anyway, we'll just call it the weight function. Fair enough. Okay, so what we saw before from 4.3.3 was that this leads us to our solution being the Bessel function. And so the 0th Bessel function is given by the series n equals 0 to infinity, negative 1 to the n, x to the 2n all over 2 to the 2n n factorial. This is what I wrote last time, and I since realized that there's a typo. This should have a square on it as well. That's a typo that's in the book as well, which is actually where I got it from, but it's wrong. And this is, oh sorry, what am I saying? That's summed over n. Yeah. Okay, and so it turns out that the eigenvalues are found by looking at the zeros of J naught. And so this is all quantity squared. And so y, the corresponding eigenfunction yn is j naught of Zn over r x, but in our case we're using the variable r, and that's n equals 1, 2, 3, where these are the zeros of j naught. And those zeros are not completely periodic. They don't appear in any nice regular pattern. They do form an increasing sequence, but that's about all you can say. So that's all I'm going to say. So then, assembling all this, we have the series from 1 to infinity of Cn e to the minus, and then whatever that eigenvalue is, kt, and then we have this times j naught of the nth 0 over r times r. And here these coefficients Cn, these are going to be given by the projection of f onto the nth eigenfunction, which is found like this. And so on top we have the integral from 0 to r of f of r j naught r Zn over r dr. And then on the bottom we have the magnitude, so that when we normalize by the norm squared down here in the bottom, that guarantees us that we're using an orthonormal basis here. So in fact our unit basis is effectively j naught of r Zn over r divided by its size. And it's worth pointing out that when we compute the integral here, so this is a unit vector. And I did this calculation once before, but just sort of to point it out, the reason why there's a factor of 2 here in the denominator is because you need one for normalizing this guy here, and then you need one for normalizing this guy here when you put it in the summation as well. And then the last thing I wanted to point out was that this guy here is the weight factor. So these guys are orthogonal when you've got the r in there, but they're not if you don't have the r in there.